Welcome back. Let us update the case setup. Right click setup and click edit. An error has occurred. CFX preprocessor is not able to import the updated models or mesh. So we can click OK. Reset the setup. Right click here and click reset. It will delete the component and local generated data. Click OK. We shall create the case setup fresh for this updated model. Now right click setup and click edit. The updated models are imported to CFX preprocessor. We can check the mesh regions, expand this. There are three regions: the external domain, the pipe solid body and the pipe internal region. Next, let us specify the domains and the boundary conditions. Right click flow analysis, insert domain, outer domain. Here this will be the outer body. I think it is B26. Click OK and check. Yes. We shall change the material property, water, change the reference pressure 0 atmosphere, fluid models, change it to total energy, let it be shear stress transport turbulence model, click OK. Similarly, create the domain for pipe internal. It is the third domain. We can click OK. Finally, we can create the solid domain. Right click flow analysis, insert domain, pipe solid. Select the solid domain, that is the second one. Here change the domain type to solid domain and the material is aluminum. We can click OK. We shall specify the boundary conditions as per the given input here for the pipe domain and external domain separately. Right click pipe internal, insert boundary, pipe inlet. The location is pipe inlet. The speed is 1 meter per second and the temperature is 80 degrees Celsius. Click OK. Similarly, insert boundary, pipe outlet. Change the boundary type to outlet. Choose pipe outlet. The average pressure is 2 bar. Click OK. Next, we shall specify the boundary condition for outer domain. Insert boundary, inlet. The speed is 4 meter per second and the temperature is 15 degrees Celsius. Click OK. Right click again, insert boundary, outlet. The pressure is 1 bar. Click OK. Next, we can define the walls. Insert boundary, wall. It has automatically chosen the wall region. Click OK. The inlet, outlet and wall boundary conditions are specified for all the two domains. Next, we have to specify the interface conditions. There are two interfaces here, that is pipe internal to solid and then pipe solid to external domain. We shall create them one by one. Insert interface, domain interface, pipe internal to solid. This will be a fluid solid type interface. And in the first region, you can select pipe internal and in the second one, you can choose pipe solid. In the region list, we have to select the pipe wall for the interface region on the internal domain. And for the pipe solid, we have to choose the pipe solid inner region. This will be the common interface regions. Go to the next tab, additional interface models, select this heat transfer and choose conservative interface flux. That's all. Click OK. Next, we have to specify the interface for pipe solid and the outer domain. That is pipe solid to outer. Again, the interface type will be fluid solid. In the domain, you can choose pipe solid for the first interface side and for the second one, it will be outer domain. In the region list, choose the pipe solid outer and in the interface side too, choose the outer domain interface region. Alright. Go to second tab, choose heat transfer, let it be conservative interface flux. Click OK. Okay, there is one more default region. Whenever boundary conditions are not defined, CFX preprocessor will name it as default region and wall boundary condition will be assigned to this. You can double click and check. The end faces are having wall boundary conditions. We can leave it as such. Now all the boundary conditions and interfaces are specified. Let us create the expression for exit temperature and start the solver. Go to expressions, right click, insert, expression, exit temperature. That is the exit temperature of pipe. Right click here, functions, locator based, mass flow average of, right click again, go to variables, find temperature, mass flow average of temperature at physical locators 2D pipe outlet. Click apply. Now go back to output control, go to monitor tab, select this monitor objects, create new monitor point, this pipe outlet temperature. Click OK. Here in the options, choose expression and select the created expressions. Right click here, expressions, exit temperature. Click OK. Now all the conditions are specified. We shall close preprocessor and go to solver. Minimize this. Right click solution and click edit. The solver window is open. It has retained the same settings as the previous case, that is without solid case. By default the number of partitions are 4 and it is local parallel. And if you go to the initial values, by default the option is current solution data if possible. It means it will use the previous result file as the initial condition and start the solver. We can start run. The solver has started. Here you can notice that it has started from the previous case. That is after 100th iteration, it is starting for the next case. We can see the exit temperature here. In the previous case, the exit temperature at the end of iterations are 344.65 Kelvin. Again, it is starting around the same value. So by this way, the time taken for convergence will come down. Alright, we can check the results after a while. The solver is complete. We can check the convergence here. Check the exit temperature. It is almost the same value. The previous case is at 344.65 and this case is at 344.35. Alright, now we can close this and go to CFX post processor. Right click results and click edit. We can see the plots retained from the earlier case in CFD post. This is plane 1. We can create another plane perpendicular to this, that is parallel to XY plane at the mid region. Z varies from 0 to 500, so we shall create at 250. Click apply. Let us see normal to Z plane. We can zoom here and select the variable as temperature. Click apply. So this is how the temperature varies. Here the scale is large, so we shall choose only the solid domain. Click apply. We can see the temperature profile variation inside the solid body. The flow living at the top and bottom regions at high velocity are resulting in lower temperature, whereas in the rear side the temperature is quite high. Next we shall check the temperature in the outer domain. Click apply. We can change the temperature range to see clearly. Go to range and choose user specified. Let the lower value be 288.15 Kelvin and the max value be, let it be 292 Kelvin. We can keep 4 Kelvin range. We can further reduce it to 290, 289. We can see the temperature range in this flow domain. Alright, next we shall go to the calculators and find out the exit temperature. Go to function calculator, choose mass flow average, pipe outlet, temperature. It is 344.8 Kelvin. We can find out the net heat transfer rate also. We can find out the heat transfer rate in any of the interface regions. In the function, choose area integral. The location, choose any of the interface. We can choose solid pipe, air to solid pipe region. Click OK and choose heat flux here. Click OK. Calculate. The value is 6055.7 watt. We can compare these results with the previous case, that is without modeling the solid domain directly. The comparison of results are shown here: exit temperature, temperature drop, and heat transfer rate. So the values are almost matching without modeling the solid domain directly and with modeling the solid domain. So this shows that for thin structures, we can directly model the fluid domains only and specify the thickness in the interface regions. I hope this would have been useful to you. We shall see some more heat exchanger problems in upcoming lectures. Alright, thanks for watching this video. I will see you in the next lecture. Thank you.